Alright, well, how y'all doing? My name is Cameron Nixon, and today we're going to be talking about how to forecast your chase using nothing but Skew-Ts, and of course my favorite, the Hodograph. So if y'all watched our video from last year, that was actually on how to anticipate supercell photogenic-ness and even behavior. So I highly recommend you check that one out after this one. I'm actually going to consider that a sequel to this one, because while I don't think this one is any less advanced than that one got to, I really want to answer the question here, where do I go to begin with? I know probably when you wake up in Goodland in the morning and grab your hearty breakfast food, and off to the 2% you go, you really want to know, where do I gotta go? And this video is going to kind of get after what I kind of use as my forecasting workflow to get out there and find the storm that I want to see. Because you're usually kind of faced with this kind of age-old dilemma here. Structure with friends or wedges. Which one do I go after? And a lot of times, a single day might have a great-looking supercell target and a great-looking tornado target. Which one do I pick? Like sometimes you get out there and you go after the supercell target because you don't think the tornadoes are going to pan out, and they do, or you go after the supercell target because you think it's going to be great, and it just ends up being this kind of grungy, dirty, icky supercell, and you kind of wish you went after the tornadoes. I really want to kind of make this decision for you better informed. Because this decision is not going to go away, and you're going to be faced with this every year you go out and every day you go out. But I'm going to hope to kind of give you some new tips and tricks to kind of help you pick which one to go after. Before we begin, though, I just want to thank every single photographer who gave their images and their content to this video. Because even compared to last year's video, there's some spectacular stuff in here. And I really hope we can keep up this kind of symbiosis, I guess you could call it, of learning from all you guys' past experiences. Because that is what we do as storm chasers. We take our experiences and others' experiences and bring in all the theory and kind of try to figure out why this happened so we could see it next time ourselves. So I really enjoy your work, and I really enjoy being able to feature it in here. And without further ado, I hope everyone enjoys the video. So what tools are you given on your quest to find the best storm of the day? Well, on the left-hand side, we got our Skew-T diagram here, which is going to show you the temperature of your environment here in red, the dew point, a measure of moisture here in green, and the temperature of your parcel here, a rising parcel, essentially our updraft here in brown. And what's really important to remember that a lot of people forget is that this temperature of our parcel here, this is our best guess based on a lot of hefty assumptions that we actually get here. So in reality, our parcel path might look a little bit more like this. We might shave off some of that cape. And it's not to say that you shouldn't trust this, but it's just important to remember that this might not always be right 100% of the time. But a lot of very useful quantities come out of here, like cape, like LCL, like LFC, equilibrium level, a lot of other things that are very important in diagnosing the environment. On your right here, we have our hodograph, and our real quantities, again, are our wind, speed, and direction here with height. This has been observed. You can also find our approximation of the mean wind using our little brown box here. And you can also find our best guess, once again, based on a lot of hefty assumptions of our supercell motion, our right mover supercell motion here. And just like our parcel path, this doesn't mean that you shouldn't trust it, but it's going to be wrong a lot of the time. We might have a supercell motion that's down here, and it might be a little bit closer to the mean wind in other scenarios, and that's going to affect values like SRH, or storm relative wind, or other things you might use to predict supercell or tornado potential. And again, these are very important quantities that fall out of here, but it's just important to remember the amount of guesswork and assumptions that go into a lot of our forecasting here. And that what you should be looking at are the actual observed values when you're making all your insights. So other things you might be handed while you're in the forecasting process are these, I just call them pretty color maps. And we got our supercell composite here. We also got SIGTOR, all that fun stuff. And I'm going to say no to these parameters today, and I hope you will too, because what we're really focused on is the actual environment here in all of its glory and all of its details. So before we get in the nitty-gritty, one of the things that's really kind of helped my forecasting game is really being able to understand how the Skew-Ts and the Hodographs change over time, how the conditions change over time in response to all the chaotic things happening in the atmosphere that lead up to a severe weather event. And like I used to just take that supercell composite map and start plucking the soundings right around tornado time 230Z, and you really don't get a broader perspective of what's actually happening throughout the day that leads up to in creating that environment that you want to be at. And if you do something like I used to do, you might actually miss key kind of failure modes or ways that the environment could go wrong or change, things that could be mistimed, and you really aren't taking into account the full range of possibilities that might be happening while you're out there. So with that, I kind of just want to take a classic Great Plains tornado environment. This was the Tescott, Kansas day back in 2018. And so what we had here, we have a pretty decently fast upper level trough here, just kind of nosing in. You can see Tescott's right around here in north central Kansas where my arrow is. And you can see the upper level flow is relatively weak currently, but just downwind we have that pretty strong jet stream max here. If we go down to 700 millibars, you can see a pretty suspect little shortwave here, and these little troughs are going to be important, as we'll talk about later. But relatively pretty weak flow. We're only rocking 20-25 knots here, and not much temperature advection here. If we go a little bit lower, you can see our 850s. We got that nice warm tongue of moisture here feeding into the Great Plains, and a pretty decent low-level jet. This is most likely a nocturnally forced low-level jet, such as are common over the Great Plains. And you also don't have much temperature or moisture advection here. But you could see a kind of northeast to southwest oriented kind of cold front dry line thing over western Kansas that's likely going to serve as our forcing. And if you look at the surface, you could also see the semblance of that forcing, even though we have pretty sparse obs here over northwest Kansas. But one of the key takeaways here is that we really don't have that much advection of anything here. And usually when we're talking advection, we have either higher temperatures or higher dew points downstream than we do upstream. And that's really not the case here. Temperatures are pretty uniform across the board here, and so are dew points. We really have 61 to 63 is what I'm seeing in Kansas right now, and that's essentially what I'm seeing in the middle of Oklahoma too. So there's not going to be that much of a change in our surface field, which might actually make this a pretty good example to go through, because there are a lot of other changes happening aside from just the surface. So picture this. It's 9 a.m. You're just rolling out of bed in your hotel in Wichita, and you're about to hit the road, checking those 12Z obs, and this is what is over Tescott right now. And this doesn't look great. The Hodograph is a train wreck. The Skew-T leaves a lot to be desired. So what's going on here? Obviously, if you plucked something like this at 22, 23Z, you certainly wouldn't be targeting this area. But I think we have faith that a lot of things could be changed about these profiles, given our knowledge of the background environment here, that could actually still yield a severe weather threat. So let's look at our Skew-T. We got a lot of CAPE stockpiled up here for 9 a.m. We got over 2,000 CAPE here. So definitely not lacking in the potential energy department here. But that's just it. It is potential energy, and we need to realize that somehow. What I'm not really digging here is that deep capping inversion here. I wouldn't necessarily call it strong, but it is deep. And what I perhaps dislike the most is just below that, we have a fairly deep layer of nearly saturated air. So what this means is as you roll out of bed, it's going to be pretty dark. There's going to be a blanket of stratus above your head that really does not bode well for daytime heating. And what's worse is this stratus is kind of just trapped right underneath that cap with nowhere to go. So while we really want that sun to poke out and to start mixing things, we really do not have that right now. So what do we have? Well, if you look just above that, there is some pretty classic dry plains-like air. So that's a good thing. That likely means that the entire rest of the sky is probably cloud-free, with the exception of perhaps some passing cirrus clouds. You can see it's a little bit more saturated up here. But what really is perhaps a saving grace about the sounding is that we do have a lot of dry air aloft, and we do have that remaining low-level jet. So what that is going to do is perhaps start mixing on its own mechanically without the need for that sunlight. So what happens when you have a fairly strong remaining jet right just above the surface is you get these rolling mixing motions in the low-level atmosphere. So what we mean by this mixing, you've heard me throw it around a couple times already. All we're going to do is just even out the low-level profiles of temperature and dew point and redistribute, I guess is a better word, the low-level values upward and the upper-level values downward. So what we do in this process is when we are dry, like we are aloft and near the surface, we're going to ride up and down these dry adibats here, these faint red lines that move up and down the Skew-T. So what we want to do is bring down some of that potentially warmer air aloft. And what we mean by potentially warmer is once we start forcing these parcels downward, they're going to be starting to ride down these dry adibats, and magically we now have a surface temperature that reaches almost 30 degrees Celsius. So that's a lot. And do I think that that's going to happen? No, I don't, because we are very cloudy near the surface, and we really, our low-level jet is going to start to go away soon. So what could we reach? Well, this 83 down here, this 83 Fahrenheit, this is your maximum temperature. You might see this on some Skew-Ts. I don't think that's going to be achievable today because of this cloud cover. However, I think we can still make a running attempt at some daytime heating because of this mechanical mixing that we got here. So I'm thinking we're going to start to ease up on this stratus deck here and start to work some magic on it. So let's roll out another hour. Looks like we've done that just a little bit. We're starting to decrease the size or the depth of this stratus deck. And while we still have that cap here, I'm starting to get a little bit more optimistic. It looks like we've gotten our surface temperature up to super adiabatic. That's higher than 9.8 degrees Celsius per kilometer. So what that means is that now our low levels are absolutely unstable. So parcels are being lifted now on their own accord. They are rising spontaneously. So that's going to generate a lot of turbulence near the ground. So what you could be seeing outside right now are these beautiful billow clouds. These kind of rolls of cloud here typically suggest mechanically unstable air and a lot of rotors, a lot of mixing going on in the low levels to kind of redistribute that atmosphere. So when you see these, the atmosphere is doing a lot of work over your area to get things prepared for later on in the day. It might succeed. It might not succeed, but I have faith. So by 16Z, looks like we've gotten rid of most of our low-level shear. So those rotor clouds are going to start to go away. And you look at this and you say, man, where'd our low-level shear go? You're watching the SRH plots and everything's going downhill. It's only 11 o'clock in the morning. Our day isn't over, is it? No, it's not. You got to remember that our low-level jet will come back. It's just one of those things that you just got to trust about the Great Plains. Our low-level flow is starting to soar at 20 knots or so as we've redistributed all the wind in the low levels, so we're going to start to average ourselves out. We're getting rid of that low level jet, but we're increasing our surface winds, and both of those things are going to shorten our shear. So we're just going to have to keep that in mind, that the low level jet's going to hopefully come back tonight, and we won't have to worry about this. But the good thing is that we're really starting to iron out these kind of kinks in this hodograph. as our mid-level flow strengthens, as this wave approaches. So we're doing work on this hodograph. We're getting there slowly but surely. It looks like our Skew-T is still looking pretty good. We've gotten rid of most of the depth of this stratus stack, however, it's still there, and we still have a pretty thick cap here. But we do continue to increase our cape, which is only going to give us some more potential energy. So as we keep going forward, looks like we're still doing a number on that stratus stack. That saturated layer is just getting really small. Come 18Z or lunch hour, things are looking a little bit bubbly now. We have those really steep low-level lapse rates. There's definitely most likely some kind of cumuliform clouds out there that might be pretty short and not very well vertically developed because we have that cap right above the LCL. But it's going to start to look a little bit better and a little bit more chaseable. So as we roll into the afternoon hours, still some subtle changes to be had. So what's happening with our little cap here as I roll back and forth between the hours? It looks like we're actually starting to lift that cap upward. So what's going on here? Well, we've got our mid-level shortwave coming through. Remember that thing, that tiny little thing that I said might be important? That is going to actually generate lift out ahead of it. And what that lift is going to do is very similar to what was going on with our mixing earlier. And so what we are literally doing to this cap is we are lifting it up. We are lifting those warm temperatures up. And when we do that, those temperatures are going to ride up that dry adiabat and physically look on the Skew-T like it is being lifted up. So this is good news if you want to get rid of this cap. Because as that shortwave comes, we're going to continue not necessarily eroding this cap, but just lifting it up and out of harm's way here. So that's just going to continue to get us our level of free convection closer to your lifted condensation level. And something you can also see, if you look close enough, right above your LCL here, it looks like that cap is moving up just enough that we're getting ourselves a little bit of leeway here beneath that cap to allow for our cumulus clouds to start getting a little bit taller. So you might see a sky that looks something like this. Our cumulus might be getting a little bit fluffier and a little bit more stocky. It might just start looking like that tornado-y sky that you want to see before a chase day. So by 20Z, looks like that cap is just a bad memory. We've got a lot of leeway now just above our LCL for clouds to start percolating. And our LFC is just ever getting closer. And so it really looks to me like we could start initiating quite soon. So checking out our satellite, that is exactly what's happening. We got that flank of towers off to your left. Things are starting to get optimistic for your chase day. So as we roll out to 21Z, that cap is just gone. We are initiating, we are breaking that cap. Those clouds are going to really have that nuclear kind of look to them because we got over 3,000 cape now stockpiled just above that. So we are going. We got our supercells. But what do we got with that hodograph, right? It's still a little bit wonky. Although our low-level shear really isn't that strong, we do optimistically have quite a bit of cloud layer shear. So I'm thinking a lot of these cells might start organizing into supercells, and we might have a few of these roaming around the area. So as our eyes are glued to the radar and we're trying to target our storm, we're going to start to see a lot of changes happen rather quickly. Get to 6 p.m. and our hodograph is starting to look pretty curvy. Looks like in just that hour we have amped up our low-level flow here, and we're starting to become a lot straighter in the mid-levels. We've also kind of started to increase our low-level shear. And all the magic's going to start to happen right around that 0Z hour as we have faith in that it will, because that is when we go through that evening transition. And so what happens there is the low levels start stabilizing. Again, we've already lost a couple degrees worth of temperature at the surface here. And so it's definitely looking like we're starting to begin that process now. And also, as that occurs, our low-level flow, our surface flow, is going to start to slacken a little bit as well. And our trusty front, the low-level jet, should come back. But we're already losing cape. You can see we're losing a couple hundred cape per hour, it looks like. So we got to make sure to do this fast before we start to become too stable. But remember, we do still have supercells in the area, and those are very good, utilizing whatever cape is still left over as the evening wears on. So it's 23Z, let's go over to that final hour. Look at what happens to that hodograph in just that 1 hour's time. This is what we all mean by zero-Z magic. That low-level jet increases and that surface wind starts decreasing. And as we go through the evening transition, yeah, we lose just a little bit of cape. However, looking at this looks like tornado time. And via Benjamin Yurkovich, it looks like it actually was. This was the gorgeous Tescott tornado, and definitely a fantastic chase day for those involved. So before we get into forecasting supercells, we need to have a quick little chat about how to forecast storm mode. I know that's not the snazziest topic here, but we need to know when we're not going to get this so that we know when we're going to get this. And there are two main kind of facets that I use while I'm forecasting storm mode, and that is the shear vector versus your boundary here, and your mean wind versus the boundary. And even though they sound roughly the same, they actually do some pretty different things. So when you have your shear vector perpendicular to your boundary, this is kind of what I'm looking for the best kind of chasing opportunities, because what that does is that kind of lines up your string of cells and they tilt down shear here in a way that does not interfere with any other storm here. You could see in this kind of configuration here with our shear vector perpendicular to that boundary, all these storms are able to coexist and kind of float on for long periods of time without messing with each other. However, when our shear is kind of parallel to this boundary here, this is how you end up getting bust scenarios. And I use this bust ironically because in many cases this can deal a lot of significant severe weather, but it's just not exactly something chasers want to see, is this massive kind of southward zippering cauldron of convection here. The other facet here is our mean wind, and what we're looking for here is a rather quick wind that blows off the boundary here. This was a substantial supercell outbreak back in May of 2008, and we were only able to get these supercells because they quickly moved off the boundary before that thing lit up like crazy. You could see all this convection here that you really don't want to be at. So we were really looking for a quick mean wind off that boundary so storms can mature before that boundary does crazy stuff like it is right here. If it's parallel, however, this is also how you get your bust scenarios because any storm is going to be just moving along the boundary and further cluttering it, and this is kind of how you end up with massive globs of disorganized convection. And to make matters worse, when you have a front that these storms initiate on that actually surges east of that storm motion, see, in this case, the storms were riding that front parallel, but now it's surging eastward. And that's just going to place those storms left of that front. And that's physically how you get undercut storms, as these kind of move into the cold sector here. So you still might get some interesting displays here. You can obviously see some tornado warnings on these, but these end up not really being the things that you do want to chase. But as promised, let's talk about how to forecast supercells. We need two major things while we're forecasting supercells, and that is instability and wind shear, and both of these play critical roles in forming and sculpting the supercell that you see here. So you're probably using these things to forecast supercells. I'm going to ask you to stop and at least reconsider. Let's chat about this a little bit. So while you're using Skew-Ts, we are looking for that instability here. And that it can be found by comparing the temperature of the updraft here in that brown dashed, which again is our kind of our best guess, with the temperature of the environment here. Because the warmer that our updraft is relative to that environment, the more it's going to want to rise. So the farther apart these two are from each other, usually the better chance of a robust updraft and a strong supercell. So you're given a lot of CAPE values and LCLs and LFCs and SYN and everything down here. And it's a very common question, well, which one do I use? Because there's a lot of options down here. So let's go through this step by step, and let's kind of remind ourselves how we got these in the first place. So all we got to do is lift our parcel here to start our parcel theory. And so what we're going to do is take our surface temperature and our dew point, and we're going to lift that surface temperature up our dry adiabats. It's cooling dry adiabatically at that 9.8 Celsius per kilometer. And again, we're going to meet up with our dew point temperature here as we're moving along the mixing ratio lines. So when we meet, that is how we get our lifted condensation level, because we condense and we're now saturated. And then we start rising by our moist adiabatic lapse rate. And we start rising by our moist adiabatic lapse rate instead of our dry adiabatic lapse rate because, you guessed it, we're moist. And what that's going to do is once you're moist, you're releasing latent heat. And that latent heat is going to prevent your parcel from cooling as quickly as it does when it's dry along those dry adiabats. And so that's why we end up well to the right of those dry adiabats once we go up the moist adiabat. It's because we're releasing latent heat on the way up. So this is obviously how you get your parcel profile, and this is your CAPE, the area between your parcel and the temperature here. And this, what we found, is actually our surface-based CAPE. We started right at the surface, and then we went up. And unfortunately, this is virtually useless because it really only considers a certain point here. So this is why you may have been discouraged against using surface-based CAPE, because it really is not representative of the environment most of the time, except for in cases where it is very well mixed. Our second kind of CAPE that we're going to focus on is our most unstable CAPE. And all this does is find the spot on the skew-t and the level at which we find the most CAPE possible. We basically squeeze out the most CAPE that we can from this profile here. So we can start at the surface. This is our surface-based parcel. We check that. We can go up a little bit more. We check that. Looks like we have a little bit less CAPE. We can even go much higher. We check that, and we have a lot less CAPE. So in the end, it looks like we found our most unstable parcel here, and that is the surface. And in most scenarios while you're out there, most unstable CAPE will approximately equal your surface-based CAPE, because usually your surface-based parcel is the warmest and the most unstable. However, when you do have elevated environments like this one here, when we have a really strong inversion, we're not going to find any CAPE using our surface-based parcel here. Our surface-based parcel ends up being much cooler than the environment at pretty much all levels here. However, this is actually going to be really important when we have elevated environments above that stable layer, because if we try calculating that most unstable CAPE again for a different layer, now we found that a level at about, 750 meters actually gives us a lot of CAPE. So this is where our most unstable CAPE is most useful. And last but not least is our mixed layer CAPE here. And this is perhaps the most realistic in determining the amount of CAPE that we actually have, because what we're doing is we're going to mix the atmosphere, which is again a very natural process, and this is most representative of what actually goes on. So after mixing, we're going to make sure our temperature goes up the dry adiabat and our dew point mixes along these mixing ratio lines. So this is generally best for most scenarios, again, because we're better approximating the natural mixing process of the atmosphere. But it's going to give us some less eye-popping numbers here. This is our mixed layer CAPE here is less than half of our surface-based parcel. But that's okay, because again, this is usually most realistic. Of course, the other facet of forecasting supercells is our wind shear, and that can be looked at using my favorite plot, the hodograph. And on the right here, we have two quite beautiful hodographs, and each produce an extremely different flavor of chase day, if you will. The hodograph on the right produced a very long-lived and violent tornado that tore through areas of Basefield and Soso, Mississippi. And the hodograph on the bottom here featured a very slow-moving, picturesque supercell in the high plains near West Texas. So what we really need to kind of remember with these photographs is that these are plots of wind with height, and that height component really matters. It's not just the shape. So what you see here is probably a pretty intense photograph. We have a lot of shear here. It's got that classic sickle shape. You're probably thinking crazy supercells today. The parameter space is all maxed out. However, if we put this in the vertical, you could see that, yeah, we got a lot of shear just below the cloud layer here. But the whole rest of the storm, we're almost calm here. We barely got any wind shear. This is good for single cells or multi-cells. So that this is a pretty common failure mode, especially when you're dealing with kind of your southeast U.S. Severe weather and tornado setups. Is that you really don't have that much shear up here, and things can get pretty messy because, again, this kind of encourages your multi-cell mode. So be careful when you're looking at your photographs here. If there's not much shear, you're not going to get what you want to see. On the other hand, you see something like this, and this might kind of be a later season or kind of an upslope regime. You might even be thinking, man, I might actually sit this one out. There's not that much shear here. There's not that much SRH. My bed feels comfy right now. And what the storm will really see with this is really strong shear where it matters most in that deep cloud layer. And so this is how you get your more kind of surprise supercell days, is because you really don't have much shear here when you're talking about kind of 0 to 6 kilometer or your 0 to 3 SRH. But again, we have really strong shear where it kind of matters most in that cloud layer. So even though we really don't use this concept of cloud layer shear specifically in our forecasts, I really want to kind of shed light on some real world examples that do highlight why it's so important for strong and persistent supercells and robust mesocyclones. This was the 2019 Denver City just drop dead gorgeous supercell here, shot by Michael Binsky. And you could see this thing, even despite that lack of 0 to 1 kilometer SRH here, this thing was rotating furiously here, and in addition to this being wildly photogenic. So my kind of secret weapon when I am going out here is this 1 to 3 kilometer shear, or just any kind of shear in the lower kind of cloud layer. And it's really good at bringing to light some more surprise scenarios. This was actually the Simla, Colorado day, and you can see how there's very weak 0 to 6 kilometer shear here on that photograph. However, if you look a little bit above, we got some pretty decent shear up to about 4 or 5 kilometers or so. So this was very likely a surprise environment, because if you're checking SPC mesoanalysis and you're looking for that 0 to 6 kilometer shear, it's probably not even going to show up on that map because there's only about 20 knots of it or so. Also, SRH probably won't be showing up much either because we're pretty small here. But as long as you have a decent amount of this cloud layer shear here, you could get displays such as this. This was Max Olson's shot of the Simla tornado here, and it's just an absolutely gorgeous supercell. So again, if you're waiting to see a certain threshold of 0 to 6 kilometer shear, you're likely going to miss out on events like this. This was the Leote, Kansas day back in 2016, and if you're kind of focused on that 0 to 6 kilometer shear, it was technically classifiable as kind of a weak shear day. But if you look above this, look at all that photograph we have. This is why it's really important to look at the full range of the photograph here and not just focus on single shears. And that this was just an amazing storm, very large, something that you might not have been able to predict just using the bulk shear. And once you get this really extreme kind of cloud layer shear here, like we have here, these can yield some pretty wild events. This was a similar photograph to one shot by Quincy Vagel here out in eastern Colorado back in 2019. And look at this thing. He couldn't even fit this entire thing in the frame with this massive panorama. This thing was enormous. And you can just get some rockin' supercells with this kind of sounding here. So don't be afraid to chase something like this, even though our 0 to 1 kilometer shear is so weak here. So do I mean not to chase weak 1 to 3 kilometer shear? No, definitely not. This was Matt Coker's absolutely breathtaking picture of this was from the Madeline and Springer, Oklahoma tornado day. I never remember which one is which. And just an amazing shot here. And again, this is just a rule of thumb. So this is something that I use to predict the presence of long-lived and robust supercells. And sometimes events can slip under that, especially for cold core events like this one was. And in return, they can yield some pretty photogenic surprises here. And this low-level shear is, as always, very good for low-level mesocyclones and long-lived and strong tornadoes. This was the base field, or maybe it's bass field sounding. I can never get that one right either. Back on Easter 2020. And this obviously yielded a very long-tracked EF4 tornado, amongst others. And so if you're a tornado buff, this is definitely the kind of photograph that you want to go for. Here is a similar shot of a supercell by Nicholas Isabella, and this kind of highlights their more distinctive character. They're a little bit less descript, and they really don't kind of have those large kind of mothershipy kind of structures, and they often occur in thermodynamics that yield some pretty low grungy LCLs, and they might have these distinctive kind of inflow bands. So environments with a strong 0 to 1 kilometer shear really obviously are your tornadic environments, and they look the part too. So if you are a tornado buff, this is the kind of sounding you go after. So what about SRH? That's important too, right? Well, actually not always. It is nice to have, but it's not actually necessary for supercell dynamics. So let's explain this. Just as a reminder, your streamwise vorticity is when your storm relative wind is perpendicular to your hodograph segment here, whereas your crosswise is when your storm relative wind is parallel to your hodograph here. And supercells need shear. It doesn't actually need to be streamwise. Here's a freak, actually, a tornado case. This is an EF3 tornado that occurred with this photograph here, spawned by a very powerful supercell here. And we obviously had very minimal SRH here. This was also just last year. This is a very nice chase day featuring a very long-lived supercell that produces a swath of large hail. And the SRH that squeezed out of this photograph really was not reminiscence of the actual threat that evolved from this. And that's because SRH is only a half of the picture here, because we do have, it's not just streamwise, we also have crosswise components of that shear. And that crosswise is still very important in sustaining supercells. And if you only use SRH, again, you're only seeing half of the picture. So that's just an important reminder that SRH is not everything, and you should look at the rest of the hodograph and that deep layer shear. Crosswise supercells can be pretty cool too. This is one that I saw down in Central Texas a few years ago. And I like to say linear shear gives you linear storms. This is a very kind of linear inflow band here, a very kind of tilted and sheared look to this. And these can be pretty cool. However, I definitely am partial to streamwise supercells born under these very large and curved humped photographs. Here is just a spectacular time lapse by Alex Sheath of the infamous Imperial Nebraska supercell. And I could just sit here and watch this for days, and I'm going to repeat this for y'all because it was just a spectacle of an event. And this is really what happens when you inject a streamwise vorticity into the veins of a supercell at all levels of the atmosphere. Your updraft is just rotating in unison in its entirety. So what about veerback? This is another common misconception amongst chasers, is that veerback is bad. And it's not actually bad, and it's been proven a few times that it is very good, actually, for photogenic tornadoes. This was just an amazing shot by Bruce Haney of the Forgan, Oklahoma tornado event back in May of 2019. And almost simultaneously, Jessica Moore was shooting this out near McCook, Nebraska. So by all means, if you don't like veerback, I encourage you not to chase setups like this because you definitely won't see stuff like this. And veerback is also very good and associated with cold core tornado outbreaks. And a lot of these can be particularly photogenic. This was actually one of Illinois' largest tornado outbreaks, and Andrew Pritchard shot this near Havana, Illinois. And just a spectacular shot. And these tend to actually be a lot more photogenic. So this all begs a question then. Is there a recipe for the perfect storm? And I've seen my fair share of mediocre supercells over the years, and I've obviously seen some jaw-dropping photos from everyone else. But I really firmly believe that this supercell out near Capital, Montana, back in 2018, shot by Nick Wegner, pretty much just takes the cake. In my personal opinion, I'm not sure you can get any more awe-inspiring than this. And to boot, this thing came with a few strong tornadoes. But the structure is just out of this world, quite literally alien. And I really kind of have been trying to kind of emulate in my forecasting, well, what environments do create this? Because I want to see this once in my lifetime, if that's even possible. So I have kind of come up with a little laundry list of ingredients that I do look for, but I kind of want to keep them vague too. And it really just kind of a moderate amount of cape can be enough for some of these events. But what we're really looking for, again, is that strong kind of cloud layer shear to really get those mesocyclone dynamics going. And that shear needs to be streamwise if you want to see those kind of barrel-shaped or mothership or UFO structures like this one was. And if you watched our video from last year, you'll also know why just a little bit of sin is also kind of required here, because that kind of helps elucidate a lot of the kind of wind-driven turbulence that gets forced up into this updraft here. And some pretty low relative humidity in the cloud layer as well is very important, because that kind of chisels away at all the external fluff around the updraft here and really highlights the core of the mesocyclone where all the dynamics are strongest. And some stronger storm relative winds are also necessary in keeping all that precipitation at bay, keeping everything crisp here, and allowing you a perfect view of that massive updraft here. But let's be honest with ourselves, we're all storm chasers. You know what we're out here for. So let's talk about tornadoes. These are an incredibly difficult process, but we can at least attempt to boil these down into instability and vorticity, and both of these being near the ground. When we're looking at instability, we are looking at the temperature of our parcel versus the temperature in the environment here in the low levels of the atmosphere, because this is where all the good stretching happens for that near surface vorticity that we're going to talk about right now. So vorticity can have two flavors, horizontal and vertical. And horizontal vorticity is when we take our environmental shear, our wind shear. The stronger our shear, the greater our vorticity is going to be, because we create that rolling motion in the low levels. And the more streamwise it is here, again, we talked about that streamwise vorticity, the better, the easier it is for that supercell to take this vortex roll and tilt it up into the vertical and stretch it right into that storm's updraft. And so that's going to be directly good for sustaining tornadoes. The other flavor of this vorticity is vertical vorticity, and this is when you already have that vorticity stacked up into the vertical, and this is just waiting for an updraft to sit above it and stretch that into a tornado. So this can be a pretty quick process, and this is kind of how you get your more haphazard and surprise kind of land spout events. This is the Denver Convergent Vorticity Zone. This is a pretty famous location out in northeast Colorado that most chasers are familiar with. And it's a very land spout and non-supercellular tornado-prone area. So it might be a pretty fun spot for some quick photogenic tornadoes. So you're probably using these while you're forecasting tornadoes. And I actually don't mind most of these, except for the composite parameter. So these make me happier. Let's talk about why. So when we're using Skew-Ts, this time we need to be focusing on the shape of our cape and not exactly the number here. So especially down the low levels, we could see that in this case, the temperature of our updraft here really is not that much warmer than the temperature of the environment here. So that's kind of what we refer to as skinny cape. And if we're not that much warmer, we're not going to be that much more buoyant. So we really need thicker cape here in order to accelerate our updrafts upward even more. So in this case here, we do have almost what could be referred to as fat cape here, where our temperature of our parcel is a lot warmer than the environment. So it's going to want to rise really quickly relative to the environment here. And it doesn't even matter that our equilibrium level is really low here, and we might actually not have nearly as much cape as we did here. But this is going to be a lot better for tornadoes, because we're starting off that low level acceleration a lot lower than we were in this case. So in that same vein, 3 cape below the 3 kilometer point can be a secret weapon, especially for days that might not have the best kind of supercell potential, or might just be a little bit more of a surprise. So it's definitely something to keep in your tool belt, especially when the rest of the setup just doesn't look that great. So this is kind of how you get your easy tornado sounding, so to speak. I typically look for 3 cape above 75 or 100 or so. And when you have really thick cape here in the low levels, this is very good for freak tornado incidents, almost regardless of what convective mode you have. On the contrary, this is what I like to refer to as a hard tornado sounding. Your LCLs are a little bit higher, your LFCs are a little bit higher, and you have not that much 3 cape here, and it's very easy to write off a sounding that looks like this because we're too dry. And we don't have that much cape in the low levels, but if you have strong enough wind shear, any supercell could still get this done, because look just above this, we have a lot of cape here. This is a very vicious cape profile for any supercell here, and this did actually produce a tornado from a long-lived supercell out in Arkansas last year. So when we're looking at hodographs, we again need to look at the shape and not just the numbers that we see. So what we're looking for our tornadoes is streamwise, low-level vorticity here. And that's, again, where our storm relative wind vector is perpendicular to that low-level shear. This can yield some pretty high critical angles. Critical angle is a decent measurement of how streamwise this shear is. So this is kind of what I refer to as an easy tornado sounding. We don't have much shear here overall, but we got some pretty strong low-level shear. And it's mostly streamwise, and all the supercells this day tended to produce tornadoes pretty quickly. This was a more surprise tornado event back in August of 2016. Whereas when our low-level shear is a little bit more crosswise like this, these might get a little bit more finicky. Not to say that these don't get the job done, and you can get some pretty strong and even long-track tornadoes from this kind of sounding. But when we're not perfectly streamwise, it might just take a little bit of extra oomph for these storms to get the job done. So when I am forecasting tornadoes, I typically try to partition these off into a couple main types, and there's obviously a huge spectrum between these. But we can think of it as supercell tornadoes versus landspout tornadoes. Supercell tornadoes are those obviously formed by supercells, and the laundry list of ingredients is such that you've probably most likely heard this before. Needs some shear, needs some low-level shear that's streamwise. Needs a moderate amount of cape, and needs some manageable LCLs and LFCs. So this is likely nothing new, and I glossed over this because you can definitely find this in a bunch of other presentations. However, we definitely can't forget that landspout tornadoes are also a thing, and this was just an amazing shot by Jim Tang out in northeast Colorado. A lot of folks called this the spout break here. And these are just classic landspout tornadoes, got that dusty look, even got a couple funnels hanging above them. So how do we forecast these? Well, they need that boundary, they need that vertical vorticity that we were talking about earlier, that was already oriented in the vertical and just ready to be stretched by any updraft that sits on that boundary. So when you have especially steep low-level lapse rates, that's going to help the low-level environment be more neutrally buoyant, and it's not going to be very stable. So it's going to be easier to lift up any circulations that form along that boundary. And especially when you juxtapose that below some pretty high cape, that is definitely when landspout potential could be maximized if you're sitting near one of these spinny boundaries here. So there's really no need at all for SRH. SRH is a supercell related process, and these landspouts already have that vertical vorticity from that boundary. You really don't need anything else in terms of wind shear. And low LCLs also might not even matter because these landspouts are really created by an updraft and really don't need that downdraft supercell process to help them out. But wait, a new foe has appeared. There is indeed another type of tornado that is very seldom talked about amongst chasers and forecasters, and that's because we really don't know that much about them. These are, I like to call them, Mother Nature's wild card. They tend to form in environments that really do not look like they could support something like this. Typically, when you go back and try to figure out what happened, you are left confounded and want to rethink your entire chase career. And to make matters worse, these can be particularly intense, even despite the rather benign environments that they seem to form in. This was the infamous Eli, Manitoba EF5, Canada's only EF5 tornado shot by Justin Hobson. And in addition to just their freak of natureness, they really have this peculiar, I like to call it suspiciously photogenic look. They really do appear kind of hyper real, like they don't really belong here. Like they're definitely not a supercell tornado, and they're definitely not a landspout tornado. So what are these? Well, it's possible that they might actually be both. I've typically heard the word hybrid being thrown around to describe these things as kind of a cross between a landspout and a supercell. But that doesn't make forecasting these things any easier. So how do you do this? Well, I've kind of learned to kind of combine my workflow between landspout forecasting and supercell tornado forecasting. And really what that means is you got to look for boundaries. You got to look for zones of vertical vorticity where everything's spinning and you're just waiting for an updraft to form on those. Then you got to look for enough cape and those steep low-level lapse rates. And you got to look for shear because we're talking about supercells here. And the end product is something that resembles both a landspout and, most definitely, a supercell. So you don't have to worry about SRH. Again, this was Canada's only EF5, rocking that sub 100 meters squared per second squared SRH. And you don't have to worry about LCLs. You can see these things are sky high, and that kind of just exacerbates the weirdness and the etherealness of these tornadoes. So there's obviously a lot more that goes on behind the scenes that we really have no idea about, and that just makes these things all the more mysterious. But that said, I really think these are kind of Mother Nature's reminder to us to just think outside the box and go after something that really doesn't seem normal to you and take that leap of faith. This was the Verdun, Manitoba tornado shot by Michaela Wasik. And this is just a breathtaking tornado. And it really, again, these just look absolutely hyper real and like they shouldn't even exist. And this is something that every chaser dreams about, and they're lucky to see only once in their lifetime. So, you know, you can chase all your life and not see something like this, but if you don't set yourself up to get lucky, you're not going to get lucky at all. So, now that we're armed with knowledge, let's put it to the test. Let's try to pick a target. This was from late May of 2018. And we're going chasing, and today, just for fun, we're just going to use this map of photographs here with cape in the background. And I do assure you, maps like this with photographs and perhaps with other things might actually become a little bit more common in your workflows in the near future as we start to kind of push these into more widely used platforms. So what we got here, we have surface vorticity here in the purple, and we got surface convergence too in green. I know there's a lot of stuff on here. Bear with me. We're trying to stuff as much stuff as we can into this map, as is my kind of signature, but sometimes it can make things a little bit messy. But these photographs should look like what you're used to. You got your 0 to 1 segment in magenta, you got your 1 to 3 in red, and so forth. So let's kind of just like ride this out and get a feel for what kind of target areas are out there. Obviously our eyes are kind of drawn to the larger cape values here, but they should also be drawn closer to kind of this convergence and vorticity, which is where we might actually get storms. Like I'm already looking at this kind of blob of cape here, and I'm probably thinking, it doesn't look like there's much in the way of surface forcing here, so this might not actually be a viable target. We'll continue onward every hour or so. Here's 4 p.m. Definitely have a lot of surface forcing, it looks like, especially in the Texas Panhandle into the Oklahoma Panhandle and Kansas. And that forcing generally starts sliding southeastward throughout the day. In general, these photographs aren't that great. I'm not thinking this is going to be a tornado outbreak by any means. But what they do excel in is this kind of deep layer, cloud layer shear, which might be pretty good for supercell storms. So we ride this out to 6 p.m. and then to 0Z, and we get a little bit more of a dramatic hodograph change as we approach that 0Z hour. Again, that 0Z magic. We start to really elongate your lower cloud layer segments. Might see a little bit stronger, a little shear as a little jet kicks in. But in general, again, this doesn't look like a major tornado outbreak. So our goal today, well, we might have a few goals. Is it find the tornado? Is it find the best supercell? Let's chat about what is actually on the table. So let's go back and let's start to pick out some soundings. Let's start to consider the vertical profile of our environment. So one place that kind of stood out to me at first glance was actually this place down in the eastern Texas Panhandle, maybe near Clarendon or McLean, because we have such high CAPE here, and we're next to a vorticity boundary, and we have decent shear here, but we just got done talking about our friends, the hybrid tornadoes. I'm actually wondering if there might actually be a shot in the dark to get some kind of brief tornadic activity because we have so much CAPE here before we turn mostly supercellular. So this is a sounding I picked from that. And yeah, we really don't have much low-level shear at all. So I'm definitely thinking a supercell tornado potential right off the bat is off the cards. But look at all that juicy cloud layer shear here. This is going to be very good for sustaining pretty large supercells. And look at those low-level lapse rates. We're definitely super adiabatic here. Things are going to get going in a hurry if we do have enough forcing, and we have some pretty thick CAPE here. So this is definitely a very viable target. I'm thinking for a quick potential spin up here before we get kind of a large supercell ongoing if we do initiate here. So interesting target. I'm definitely kind of eyeballing that. As we scroll outward, I'm starting to like this area too. Up in Kansas, we have a little bit stronger of kind of a forcing and surface vorticity boundary. So, and if you remember anything about the day, we did have the potential for upscale growth rather quickly, and that is because we have kind of a mean wind vector. These are drawn in that black here. That is roughly parallel to this convergent boundary. And again, if you remember from the beginning, once our mean wind is roughly parallel to that boundary, and some of our shear vector is roughly parallel to that boundary as well. So this might be a rather quick target to grow up scale. So we're definitely going to keep that in mind, but we're still going to plop a sounding here because I'm curious. And this is a little bit improved. Look at all that curvature in the hodograph here. We have a lot of cloud layer shear, and honestly, this looks like a wildly photogenic supercell hodograph if it weren't for the lack of sin here, if it weren't for kind of that deep saturated layer here. That there's a lot that is actually going against photogenic-ness here in the thermodynamic profile, but this does actually seem like a little bit more viable of a tornado target, because not only are we near a very vorticity-rich boundary, but we have a decent hodograph profile, perhaps just enough shear for tornadoes on the surface. That's asking a lot, but I'm thinking that vorticity boundary might be able to make up for it. We have a lot of CAPE just below 6 kilometers. We have almost 1,000 of it, so that's definitely encouraging for perhaps a quick couple spin-ups before things grow upscale. So this was another target I was looking at. It's a little bit farther removed, so it might be a little bit more isolated. Let's check out that sounding. Low-level shear is definitely lacking, really not much more, perhaps even less than the case before. In general, shear seems a little bit weaker. LCLs seem a little bit higher too, and given that it seems to be also away from the main zone of vorticity here, this really does not seem like a viable target for me anymore. I might just kind of throw that one out. So if we continue onward, I'm starting to think that this area over here in northeast Oklahoma might initiate. So let's pluck a sounding from roughly around the initiation time here. And this is interesting. All these soundings have characters today, and this is a real world example for sure, because nothing here seems to be quite right. Our LCLs are sky high here, and this is not going to bode well whatsoever for a supercell tornado potential. The low level shear here, all the way up to 3 kilometers, is very weak. Yeah, you do have some strong kind of ventilating shear in the upper levels here, but all of our good kind of supercell shear down here is really minimal, and our cape is good here. But I'm almost thinking if we initiate, even at 5 o'clock here, if we initiate in this profile, we're gonna get bombs of rain. You can see this is our downdraft parcel right here. This is how we calculate D cape, downdraft cape, and it essentially what this means is our downdrafts are going to be a lot cooler than our environmental temperature. That's 55 degrees potentially. Versus our 90 at the surface. This is just one way to tell the strength of your downdrafts, in addition to just knowing this kind of inverted V look. So I'm thinking any supercell that forms here, if we don't wait till 0Z to initiate, if we initiate any earlier than that, things are going to start to get pretty outflowy and pretty wet, pretty windy. I'm intrigued because a target like this would kind of send out a supercell ahead of everything else and into some of those better hodographs, as you saw around 0Z. So I can't give up on this yet. But initiation might get a little messy. So continue out a little bit. I am kind of wondering what may happen if we do sustain a supercell out there by 0Z. So let's take a look at that. And this is dramatically different. We have a lot of cloud layer shear here, where it matters most, especially in those low levels. Our tornado shear here in the low levels is not great. So I'm pretty much writing off a tornado threat here. But I really can't be convinced not to chase this because of how much shear that could potentially evolve later on in the afternoon. This is definitely something that might yield some pretty powerful supercells as we get around the 0Z hour. I'm just, again, concerned by how quickly this environment evolves and the initial storm mode here. And you can see our thermodynamic profile, again, is just very bad for tornadoes. We have that icky inverted V sounding here, and we still have a lot of that downdraft cape. So again, I'm kind of writing off tornado potential, but I'm still kind of intrigued. This is definitely a sounding for a pretty robust supercell potential. So I also kind of like the idea of this target again. We were thinking about that brief spin-up potential before we get kind of a more longer-lived supercell, given the strong shear profile here. So if we kind of assume that a supercell like that is going to last into the evening hours, I'm just going to pluck a sounding here to see what it might look like by 0Z. And this is just your classic dry line oven sounding. Look at your LCL is above 2 kilometers or so. You're really dry throughout the column too. This is you're under 20% relative humidity here. This is just your oven style of a sounding. 94 degrees is your surface temperature. Obviously your low level shear is nothing, but you do have a decent amount of cloud layer shear. Even a bit of streamwiseness in the low levels, which could make for some a little bit more rounded structures. Things might get a little bit interesting. It's always nice to have those really high base storms. Could have like a flying saucer or something with something like this. So I would write this target off. I personally would not choose this target. Just for the fact that it really seems like a shot in the dark to get any sort of tornado or a spectacular supercell event. So you probably wouldn't find me here. So how do we do? Well, it looks like with the prevalence of hail reports and hail swaths, there's definitely no shortage of supercells out there today, which was entirely expected. Also, it looks like all three of these targets, except for the one that we kind of wrote off, actually produce tornadoes, which is kind of cool. Looks like we even got a quick tornado in the beginning from this cell over here. And it looks like that vorticity boundary was doing some work up here with a couple tornado reports. Even looks like this massive thing here also produced a tornado. So let's check out our reflectivity and how that went throughout the course of the day. You can see this part of the boundary initiated pretty early. There's a lot of forcing up here, so that's not really surprising. It looks like we got a lot of competition too with that mean wind and that shear vector parallel to that boundary. So things are getting messy pretty quick, and it's only 5 p.m. However, looks like John Serlin here was able to capture this beast of a tornado. Definitely has a little bit of that grunge factor that we talked about with those more saturated low levels here. But our cloud bases are actually pretty high, and this to me looks pretty photogenic. So job well done. Looks like John and everyone else who chased up here had a fantastic time. So if we keep going out, look at that beast of a supercell down here. Just look at the shape, even from this low-res reflectivity mosaic here. And look at what's feeding into it. All those kind of low-level surface boundaries are kind of all pointing in its direction here. So I'm wondering if just before this, this is kind of the reason it might have been able to produce that report, if it was legit or not. Also look at that northern target. It's only 23Z, and we're full on line here. You can also kind of see the intersection of a couple boundaries here, perhaps. So something going on with all that vorticity up there too. And in between that, you could also see a rogue isolated supercell here that's already gotten pretty big. Scoot that forward, and man, that northern target is done. Chasers up there are done, but the ones who saw a tornado probably had a pretty good day. This supercell is still ongoing, and look at all that garbage it left in its wake. This is a massive blob by 0Z. However, it looks like there were actually a couple. This supercell grew a buddy, it looks like, supercells down here near the Oklahoma border. And this was actually a storm that the Tornado Titans were able to see. And just look at that. It is a cool, definitely your classic Western Oklahoma dry line. Really high-based LP, even has a little bit of that UFO kind of look to it. So definitely turned out to be a pretty worthwhile target. And this was me on the Waynoka, Oklahoma supercell. And this thing was certifiably a beast. It definitely had an extremely powerful RFD. There's lots of rain and wind in that thing. I definitely did not get close enough to see whatever tornado was reported. I actually have seen pictures of it, so it does exist. But if you do like supercell dynamics, this thing was a pretty powerful supercell. So I'm not regretting that decision to see this thing because this definitely kind of made the most of that sheer environment. So with that, I'll have Dr. Jeff Frame's fantastic photo of the Bennington, Kansas tornado. Bid you to be safe, learn a lot, and have fun out there. Thanks for watching, folks.